4 talks to be given by Gábor from the Alfred Renouy Institute of Mathematics in Budapest. Over to you, Gábor.
Yeah, thanks a lot for the invitation. So stop me if you have questions. I think that's completely okay to ask. Because I'm not sure what your background is. So I may start talking about something that you don't know. So stop me. So the topic of the whole series is probability on Kazhdan groups. To start that, so of course we will do different stochastic processes like random walks and percolation and other statistical mechanics models on the Cayley graphs of Kazhdan groups. So for me, groups will be countable, finitely generated groups. I write that down. So gamma is countable, finitely generated. Is the size okay? Okay. So gamma is countable and finitely generated. Okay, I need to talk about some, well, maybe I don't need, but so let's start with some things that hopefully you all know, which is amenability and non-amenability, and some graph theory stuff, which is sort of one, for me, is one motivation for Kazhdan groups, like expander graphs. So the thing that you probably know, so what is your, so gamma is amenable if, what is your favorite definition? Sorry? Fellner sets. Okay, let's start with the first one, just for for historical reasons. Okay, so what was the first one? Yeah, so von Neumann. Uh, 29. There is an invariant. So this is invariant. Okay, finitely additive probability. Okay, either we talk about means or probability measures on the whole subset of the group. Probability measure. Okay, maybe I put it in quotation marks because it's only finitely additive on all subsets of gamma. Okay, so everyone knows what this is? Good. So Fellner, 55. There is a sequence of subsets, finite. Okay, sorry. Okay, I have already messed it up. So Fellner 55, 1 or any of the Cayley graphs where should I write it? Okay, finite generating set. One or any of the Cayley graphs is Fellner. Okay, Fellner amenable. Okay, has, okay, let me write the definition. Has a sequence of subsets with vanishing boundary to volume ratio. Okay, and okay, let's say for me the boundary will be the edge boundary. So the set of edges sticking out of Fn. Okay, and by the way, so for any, let's say, bounded degree graph, this is the usual definition of amenable. For instance, a tree is amenable, just a general tree is amenable if and only if there are arbitrarily long like hanging chains, so sequence of degree 2 vertices in the tree. In a transitive graph where you can translate sets, you can also require this Fn to be an exhaustion. So like it's an increasing sequence of sets converging to the vertex set. You can add that requirement on transitive graphs. Okay, next one. Fixed point of affine actions. Don't know who said it. Yeah, fixed point of affine actions. Okay, I don't need that, so I don't try. Anything else? Okay. So Kazhdan 59. So who knows this? 1, 2, 3, 4, 5. Okay, so I have to say it. So Kazhdan 59, which was the PhD thesis of Kazhdan, which is he looked at random walks on groups, and well, he looked at so Pn. So consider so simple random walk on G, and let's look at the return probabilities. So Pn(xx), okay, in general, Pn(xy), by definition, is called the discrete heat kernel. Is the probability that if we start the random walk at vertex x, then at time n we are at y. Okay, and then we can look for fixed x and y, most often for just the diagonal terms, so xx, the return probabilities. How do they decay in n? So, okay, now, so if it's a Cayley graph, okay, usually I will assume that it's symmetric generators, so it's an undirected, naturally an undirected graph. Okay, if it doesn't contain the identity, because why would it contain in a group? You don't need it as a generator. Then you don't have loops in the Cayley graph. So after an odd number of steps, you can either come back or not. The Cayley graph may be bipartite. If I don't want to deal with that, let's look at then just return times and even times. Now, one simple observation is that these return probabilities are super sub something multiplicative. So let's write it. Right, so the probability of being back after 2n plus 2m steps, one particular way of doing that is to be back after 2n steps and then be back after the next 2m steps, which means that if I, okay, let's also notice that P2nxx, okay, let's give a lower bound. Of course, an upper bound is 1, okay? A lower bound. So whatever you did in the first n steps, in the second n steps, you can reverse that. So, and then you will be back. So D is the degree. Of the graph, of the transitive graph that I'm usually talking about. So here is the size of the generating set. Okay, which means that if I take So an would be minus log p2n x. Then so an is a subadditive. And an is always between 0 and log square root of d. Is it right? Something like that. Let me check. Okay, so Fekete's lemma. I don't know if you call it Fekete's lemma, the subadditive convergence lemma. Says that if you have a subadditive sequence and it's you don't have a plus infinity, that's the point here. Yep. It converges to something. In log between 0 and log square root of d. And doing back the exponentiation, lim n 2nth root of p2nx exists. Okay. And that's called the spectral radius of G. Okay. So this is a number between 1 over root d and 1. Okay, so this is just the thing. And then you can ask, so if it's 1, then it means, right, that these probabilities decay sub-exponentially. If it's less than 1, then they decay exponentially. And that's an important question about the random walk. So maybe the first thing you have seen about random walks is on ZD. What is the order of magnitude of the return probability? Do you know? Okay, I don't hear it, but I'm guessing you are guessing right. Right, more or less you have to be back in D coordinates, kind of independently. And in one coordinate by the local central limit theorem is 1 over root n. Okay, so it's polynomial. So there, the spectral radius is 1. On the deregular tree, I don't know if you have ever calculated it. I'm not going to do it. 2 root d minus 1 over d. So there is some recursion that you can write, and because of the tree structure and with something generating functions or something you can calculate it. It's less than 1 if for d equals 2 is of course 1, but for when d is at least 3, less than 1. And Kazhdan's theorem is that amenable is the same as rho being 1. So decaying sub-exponentially. That's amenable. Okay. Why is it called spectral radius? What does it have to do with any sort of spectrum?
It's a graph statement or a proof statement?
Okay, it's a graph. It's a graph statement. So Kazhdan proved this for groups. He also proved that this is the smallest spectral radius you can get, and if it's this, then it is the free group. Well, or the Cayley graph of the. Right, you can get the deregular tree not only from the free group as a Cayley graph, but also right. So for instance, if you take the 3-wise free product of the group on 2 elements, you get the 3 regular tree. So it's really and it's not only a graph thing, it's a Markov chain thing. So let me write, and I think that's the proper definition because that's the proper generality in which it holds. So let me write that in that generality. So why is it called a spectral radius? Okay, so consider any reversible Markov chain. Okay, if you don't know what reversible Markov chain means, it doesn't matter. What is really a reversible Markov chain? It's just random walk on a weighted graph. So the transition probabilities for the Markov chain are all given by some conductances on the edges. These are called conductances. It doesn't matter if you haven't seen electric networks. So these are symmetric. So, okay, let me write that down. So symmetric non-negative numbers on the edges. And then we define a biased random walk, biased according to the weight. So the probability from going to X to Y is the conductance divided by the sum of the conductances going out of X. Okay, and then and the point is that so for this Markov chain, it's easy to write down a stationary distribution. Sorry, not a distribution, a stationary measure on an infinite graph. So if you just think of an infinite unweighted graph, a Cayley graph, then these conductances are all ones. The sum of the conductances in a vertex is just the degree. And what is the stationary measure? The constant anything. So, but it's not a stationary distribution if the Cayley graph is infinite. No. Is a stationary measure, moreover reversible, and that's the definition of moreover reversible, which means that if you run the chain in stationarity from the stationary measure, then sort of the frequency with which you see a transition from X to Y, this is that, right, is the same as seeing the transition from Y to X. Okay, this is obvious to check from the definition. Okay, so whenever you have a reversible Markov chain, then you can look at functions on the, let's say, real functions on the vertex set, and you can define an inner product. With respect to the stationary measure. And you can look at the Markov operator. Okay, just by this, you can check that P will be self-adjoint with respect to this inner product. By reversibility. Okay, you can also see that it's a contraction in whatever norm you want, say the L2 norm. Okay, maybe, shall I write that? So who has seen in some form that this P is a contraction? Okay, so I do say it. So okay, so it's an averaging operator, right? You take the average with respect to your neighbors in the random walk. So you could write this, so it's called Markov operator. You can think of this probabilistically as starting a random walk at x and take one step and average the function with respect to the one step. So it's right, the expectation of so start the random walk at x and make it one step and take the average. Okay, and why is it a contraction? So let's calculate this the norm. So after one step, right, if this is the sum over x's, pfx squared times pi of x. Okay, what is this? Well, that's the definition. So it's sum over x, sum over y. What? Something is. Okay, we'll see. So pfx, so pfx is this, right? So this is pfx. So we have to take the square of this to get pfx squared. Okay, now, okay, this is an average, and this is a square. So Jensen's inequality. Okay, we have a double sum, so we switch them. So the sum over x, okay, this comes out pxy. Okay, let me write it here. So sum over x, pxy, pi of x. Right, so pi is a stationary distribution. So starting from x and making one step, what is the probability that I'm in y? well, it's not a probability, it's a measure, but okay. So stationarity means that this is pi of y. So it's the sum over y of pi of y fy squared. So it's the square of the pi norm of f. Okay, almost. Right. So the norm of pi of f, p of f is at most the norm of f. So it's a contraction. So its norm is at most 1. Right, because what is the norm of an operator? Well, you know, but let me say, so, okay, actually, let me say it as a lemma, what I want. So for self-adjoint, P, okay, so that's, okay, the definition of the norm is the supremum of the ratios. Okay, this you know. But also the lemma is that it's okay to, so instead of taking the inner product of PF with PF, you can take F with PF. So if you think of a symmetric matrix, let's say, just a finite symmetric matrix as a self-adjoint operator with respect to just the counting measure, okay, what is the norm is the highest eigenvalue. So here you get, right? Okay, there are square roots, right, in the inner product. So it's lambda. And here, if f is the eigenvector corresponding to the largest eigenvalue, then this is lambda times the square of the length of the vector. So I have to divide by the square of the length of the vector, and I'm still getting the largest eigenvalue. And this is true also not for matrices, but really for self-adjoint operators as well. Right, and so we see that this norm is at most 1. And there is something called the spectral radius theorem. For self-adjoint P, the norm is actually, you can get it as sort of you take, there is again some sort of sub-multiplicativity as in the return probabilities. So you actually, the norm is like, is the infimum and the limit of these, the norms of the nth powers 1 over n. And this is the spectral radius of the operator, which is the smallest radius in which, in the complex plane, all the spectrum of P is contained. But anyway, the point for us will be that actually the norm of P is the same as this spectral radius. And because for a reversible Markov chain, you get, I mean, it is a self-adjoint operator, the Markov operator. It is, you know, this is very similar to what we did before. So it is not hard to see. There is a little bit of work, but not much. It is not hard to see that for for the Markov operator of a reversible chain. The spectral radius in the norm is what the probabilistic meaning of this. So it is the lim, what we had before, the 2nth root E2n xx. Okay, so the point of this all was only that this spectral radius that we easily defined from the random walk itself, it is called the spectral radius because there is this Markov operator, which is a self-adjoint operator, and it is the spectral radius and the operator norm of the operator, of the Markov operator. Okay, so, okay, let me check if I didn't forget anything. Good. So examples. So amenable groups. Okay, well, ZD is an example, either because the Fellner sets are obvious, the n by n boxes, or because of the polynomial decay. Okay, I don't try. So, okay, what other amenable groups do you know? Yes, good. So for a probabilist, the Lamplighter group is the example for everything, most typically the counterexample to everything. So what is the Lamplighter group? So take it's a solvable group. So if you know group theory, it is already von Neumann proved that groups you can build from amenable groups with a direct product, semi-direct product, group extensions, things like that. They are all amenable. So solvable groups are amenable. This is a solvable group. You take the Lamplighter group. So you take a street, which could be a big city even, so a group. In case of a city, it's just Z. And on each corner of the street, there's a lamp, which can be either on or off. Or in more complicated situations, you can put any group that you want there. So your lights have a group structure. So simplest case is that the lights are on or off. And so on each vertex of Z, you put a copy of V2. So in this sum, I mean only finitely many lamps are on. Okay, so only finitely many ones. Maybe it's called the restrict. I don't know. Maybe that's the usual definition notation. Is it okay? So only finitely many non-zero terms or elements. Okay, but I'm not done yet. On this direct sum, Z acts by translations, obviously. So with respect to this translation action, you can take the semi-direct product. Okay, so it's If you cannot read, it's okay. I wrote action by translations. And if you don't know, if you haven't learned or have forgotten group theory and you don't know what a semi-direct product is, doesn't matter. A standard Cayley graph of this group is just the following. So, so you have the street. You have some lamps that are on, finitely many. Okay, let's say 3 lamps are on. There's a lamplighter. This is the that coordinate. So here is a girl standing. She is the lamplighter. So this is one group element. This is this configuration, the lamps with the lamplighter, and 3 generators. The lamplighter can switch the lamp where she's standing now. So just addition of Z2 where she's standing. That's one group element, one generator. Or she can go 1 to the right, or can go 1 to the left. So 3 generators, left, right, switch, where you are, where the lamplighter is. Okay, and so from the identity element, which is all the lamps are off, okay, let's say there's a 0 element in Z, and the lamplighter is standing at 0. You can, in finitely many steps, you can get to any configuration. So that's the Cayley graph of this group with respect to these generators. If you have learned what a semi-direct product is, but not comfortable with it, it's a good exercise to check that this is indeed a Cayley graph of that semi-direct product. Okay, why is it amenable? Okay, so what is the Fellner sequence? So lamps can be on or off only between -n and n. Sorry, they can be on only between -n and n. And the lamplighter has to be standing between -n and n. Okay, I don't write it. So okay, so only between -n and n things are on, and the lamplighter is. Oh, okay. So that means that nothing was audible for the recording until now. Okay, easy. Okay, so this is a finite set. What is its cardinality? Well, there are 2n+1 places for the lamplighter, and 2 to the 2n+1 possibilities for the lamps. Okay, what is the boundary of this set? Well, you can get out of this set only by the lamplighter standing at the edge, at this vertex or that vertex, which are 2 times any possible configuration inside. And then she has to go here to the left and here to the right. So the number of edges sticking out is just 2 times 2 to the n+1. Okay, so the ratio between these two goes to 0, so it is a Fellner set, Fellner sequence. Okay, so exercise, Okay, they are due tomorrow before class. No. So if you wanted, so this is by the Fellner definition. If you want to check the Kazhdan definition, the return probabilities, if you want to show that it's amenable, then we have to give a sub-exponential lower bound on the return probability. So you need to cook up a strategy that lasts for n steps, and a strategy. So with high probability, a sub-exponentially high probability, you are back at the origin with all the lamps off. Okay, maybe. Okay, this is not this is not bipartite, so I don't have to worry about the. But anyway, a constant times e to the minus another constant times e to the 1/3. Okay, it's a very nice exercise. So if okay, with 1/2 it's easier. With the 1/3 it's a bit harder, but you need to know a bit more probability. But even without knowing much probability, the 1/2 is doable. So indeed, it's and actually that's the truth. So the upper bound is harder, but that's the right decay. Okay, finite groups are of course amenable. Okay, non-amenable. Examples, the free group. Okay, or the Cayley graph. Okay, so depending whether we're talking about groups or graphs, so trees. What else? So any group that contains a free group on two elements. Okay, why? Why is it non-amenable? Due to? Okay, okay, that's one possibility. Yes, yes. So, so if you have this, you can have some paradoxical decomposition, and then it cannot have a invariant mean. So that's one thing, one way of seeing it. So actually, if you have any non-amenable, so let's write that, and then not so. So if you have any non-amenable sigma as a subgroup of gamma, then gamma cannot be amenable. Why is that? Okay, that's harder to say. So, the Fellner sequence, it's unclear. I mean, you have this big group inside the smaller group is sitting. How do you construct? I mean, and assume that gamma is amenable. Does sigma inherit a Fellner sequence? Especially, okay, if it's a finite index, then yes. But if it's an infinite index, it's completely unclear. The index is like how many times, the cardinality of the factor. Okay, I didn't say because I forgot, but so okay, I did write that in the Fellner definition, one or any Cayley graph doesn't matter. If in one finitely generated Cayley graph, if with one finite generating system, the Cayley graph is Fellner amenable, then in any other finite generating set, the Cayley graph is amenable, because you can just write each generator as a product of the other generators, and you see that the Cayley graph didn't change by much. It's quasi-isometric. The two Cayley graphs are quasi-isometric to each other. And this boundary to volume ratio didn't change only by a factor. So a Fellner sequence is still a Fellner sequence. So you can go between finite generating systems easily. Now, so what about infinite generating systems? Sometimes they are worth looking at. Why? Because so imagine that sigma is so you have some Cayley graph of gamma. And a subgroup sigma is sitting inside the Cayley graph of gamma. Okay, it looks something like this. If you run a random walk on gamma, okay, let's say this is the identity. That's the same in both groups. So if you start running a random walk, then it will get out of sigma, of course, but maybe it will come back sometimes. And because of transitivity, if you are just recording the times when it is back to sigma, it is a different Markov chain. It is still a Markov chain, right? The returns to sigma. Maybe it's actually right. Sigma doesn't have to be recurrent inside gamma, so it's possible, right? If it's you know, think of just sigma maybe is just one Z and gamma is a big non-amenable group, then it may be that after the identity, sigma is not visited anymore. So it's a Markov chain when not coming back ever is a possibility, like getting killed is a possibility. But otherwise, it is a Markov chain, and we can look at the return probabilities in this Markov chain. But now the jumps are not necessarily bounded degrees, right? I mean, you can have, maybe you can go anywhere inside sigma through elements of gamma. So that's why the lemma that I'm going to write is interesting, which is if gamma is non-amenable, okay, is a finitely generated non-amenable group, then for any transitive Markov chain on it, the norm is still less than 1. So you sort of, even with infinite generating, of course, if I take an infinite generating set, then I cannot just take the simple random walk because it doesn't make sense to pick uniformly at random from infinitely many neighbors. So that's why I'm saying any transitive Markov chain. So you have some transition probabilities, and this set of transition probabilities is the translation invariant in the Cayley graph on the group. But there is still a Markov operator, and its norm is will be less than 1. You cannot make gamma look like amenable by taking long jumps. And the reason is very simple. If you want, that's another exercise to prove. Like this Markov chain, any Markov chain, you can approximate by taking a large finite jump Markov chain, and that large finite jump Markov chain still will have norm less than 1, because for finite generating sets the transition is okay, and using that you can also prove that the original one was.
Any Markov chain you always restricting yourself to irreducible.
Sorry? Oh, reversible.
No, irreducible. Like
Transitive, like you just
Yeah, reducible is fine as well. I mean, it becomes smaller.
stuff, right? Cannot just move the Markov chain at all, then you have number of equals to 1. Right? So you mean the underlying graph could be connected, right?
Yes, yes. That generates gamma. Yes. Yeah, so by transitive, I just meant translation invariant. I didn't mean, that could also mean this actually, because, okay, anyway. Okay, and because of this, so this induced random walk on sigma, so if this, what? Yes, 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 yes. 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 Okay, so yeah, so I mean, the last part is simpler actually. I mean, the return probability. So you are back with the random walk inside gamma, if and only if you are back in the induced random walk in sigma, right? Because you have to be back here. Okay, so so if this is non-amenable, then these return probabilities decay exponentially. So the return probabilities in gamma decay exponentially, hence it is non-amenable. Okay, I have no. Okay, I'm not sure I want. So.
You also need a finite Markov chain approximate. They have spectral radius uniformly bounded.
Yes, that wasn't a complete proof. I agree. Okay, I don't remember right now. For sure. There is a small trick you have to do. So, catch-up proofs of the equivalences. Okay, let's write it like this. Okay, right. We had 3 definitions so far. There will be a percolation theoretical definition of amenability as well. Late, probably tomorrow or Wednesday. Okay, but so far we had the three. Invariant means, Fellner, and return probabilities. Okay, so how do we get from Fellner to von Neumann? Okay, so maybe everyone has seen that. Right? We define mu n. So we want for any subset of the of gamma of the vertices, we can define the nth measure of A as the cardinality of A inside the Fellner set, normalized by the size of the Fellner set. Okay, that's between 0 and 1. So that's a bounded sequence for any A. We should take some limit of this. What kind of limit? An ultrafilter limit, yeah. So, okay, sorry for, okay, my general attitude towards such things as ultrafilters would be that, what? This is some nonsense. I hope I will have time. The last lecture, I will actually, okay, there's a proof when I actually need to, actually also here you actually need to use something like ultrafilters. So they are useful, at least to make things more elegant, but sometimes they are necessary. So, because here, you cannot take a limit because it's just a bounded sequence. You have no idea if it converges. You cannot take lim sup because that won't be finitely additive or lim-inf. So you have to take some actual limit. So take a non-principal ultrafilter omega on n. Okay, so who knows what a non-principal ultrafilter is? Okay, so it's a set of subsets of n. So a set of subsets of n, and something is in the ultrafilter if it's large. So it's a notion of largeness. So the empty set is not large. Everything is large. More generally, for every A, maybe let's not call it A, for every S in N, either the set is large or its complement is large. Okay, if S is large and T is even larger, then T is also large. That's the filter part, I think. Okay, if you intersect two large things, it is still large. Okay, I guess this is some sort of maximality. Okay, this is also the filter. Okay, non-principal ultrafilter means that there are very simple ultrafilters, which is take a finite set, just a singleton, let's say, and every set that contains that finite set is large. So taking so generated by a fixed finite set, right? If both sets contains it, then the intersection contains it. The others are equally trivial. So non-principal is so not generated by a finite set. Okay, and non-principal ultrafilters exist, but you need the axiom of choice to produce them. Maybe it's equivalent to the axiom of, probably it's equivalent to the axiom of choice that they exist. And then, so once you fix your ultrafilter, okay, so let's say they exist by axiom of choice. And once you have an ultrafilter, you can take an ultralimit of the sequence. For the MNAs. So how do I? So for any bounded sequence, so if you fix your ultrafilter, then any bounded sequence will have a limit. That's the point. So how do I take the limit? You cut 0, 1, right? These numbers are in 0, 1. So you cut your interval in the middle, in half, and you look at the set, you look at the numbers mu and a. So you fixed your a as well. So I'm taking only the limit for 1a. So there is a subset of the ends that go to the left, and some others, and the complement goes to the right. Exactly one of them is in the ultrafilter. Take that one. So let's, I don't know, N1 is the set of ends such that mu n a, sorry, what? So let's say, okay, left one is the set of ends where mu n a is less than 1/2, and right one is the set of ends where mu n a is at least 1/2. L1 or R1 is in omega. So take that one. You have many things here. Now cut that into two. Either this half or that half, by the finite intersection property, will also again be large, and the other is not large. So take the one that is still large. Cut it into half, take the one that is still large. Cut it half, take the one that is still in omega. There will be a unique m omega a, mu omega a, such that, okay, let me write it here. So there is unique mu omega a in 0, 1, such that for every epsilon positive, the set of ends such that mu n a minus mu omega a is less than epsilon is in omega. So that's the ultralimit of these numbers. And then once you have these numbers, it's very easy to check that it is an invariant mean. So what do we need? We need that it's translation invariant. So if I translate A by a group element, then these numbers for large n, right? These numbers will be very close to each other because of the Fellner property. So that if they are very close to each other, then it's very easy to see that the ultralimit must be the same. So you will have the same. But I mean, if you have two sequences that are sort of converging together, maybe they are not converging, but they are closer and closer to each other, then their ultralimit must be the same. under any ultralimit, under any ultrafilter. And if you have two disjoint A and B, then these finite things are additive. The limit will also be additive. So it is a finitely additive probability measure. So let me just record that easy to check. That it's finitely additive probability measure, invariant probability measure. Okay, from Fellner, it's also easy to check that the Kazhdan, that the spectral radius is 1. So take a good Fellner set. So boundary to volume ratio is less than epsilon. Then, okay, let's calculate. Right, what is in this Kazhdan view when the operator norm is 1? What does that mean? On a finite group, on a finite Markov chain, the operator norm is exactly 1. I didn't say that. Why? Because the constant 1, you can put that on a finite Markov chain. This is in L2. So, no, okay, let me. So, note. If there is a stationary distribution of the Markov chain, so if the total measure of the state space is finite, then the constant 1 is in L2 of I don't know, maybe it's little L2, I don't know which is the better node. Okay, so it is in L2 with respect to pi, the constant 1. And if you apply p to the constant 1, you get just 1. So it's actually a right eigenvalue with eigenvector with eigenvalue 1. Hence, and we know that. So 1 is indeed, I mean, and the rest of the spectrum is inside 1. So indeed, the operator norm is 1. So when we say that amenable means that the operator norm is 1, that sort of means that we want almost invariant functions, not invariant functions, but almost invariant ones that show that right, that p, if we apply p to the function, then the norm of this should be pretty much like the norm of the original one, right? So this ratio should be large. If this ratio is arbitrarily close to 1, then the norm of p is 1, right? So, and if we take a large Fellner set, the indicator of the large Fellner set, you know, what does p do to it? On most of it, it remains constant 1. Only on the boundary, it gets blurred a little bit. So it should be an almost invariant function, and it is. You can easily calculate. Okay, let me not do it. It's, I guess it's just put in, and it's 1 minus epsilon squared, if I remember correctly. Yeah. Yeah. Okay. It's harder. How do we get from Kazhdan to Fellner? So Kazhdan amenable means there are, the norm is 1. So there are almost invariant functions, but we have to produce almost invariant sets because that's a Fellner sequence. So if you have an almost invariant function, how do you produce an almost invariant set? You can try to take, you have your function, you take a level set and everything above a level, and you hope that one of these level sets or upper level sets will work. And yes, one of them will work. Okay, how do we prove that this is the case? So assume non-Fellner. So that means that the Cheeger constant which is the infimum of the boundary to volume ratios, okay, sorry, don't write anything. So I want to do this in the generality of Markov chains, because this is the generality that I actually defined at Kazhdan. But then I also should properly define the Fellner being a Fellner set in the, actually already here, right? I should have done that. So I should properly define what a Fellner sequence is, or what is the Cheeger constant in a Markov chain. So instead of just taking cardinality, what do I do? So I take, okay, so volume is just the stationary measure of the set. And what is the boundary? The edge boundary, the probability, the measure that goes out. So X is in S and Y is in S complement. I'm at X with probability, with measure X, with measure pi of X, and I'm going out with probability Pxy. So this is the Cheeger constant, and we assume that it's this is positive. This is being non-amenable in the Fellner sense. Okay. Okay, so I want to prove that I want to prove non-Kazhdan, right? So for any function, I want this to be bounded away from 1. So let's look at the gradient of f. Okay, what do I mean by that? So along an edge, okay, so this is like a discrete differential geometry. You have a function on the vertices. What is the derivative? Well, it's a function on the tangent bundle. It's a function on the edges, right? And how should I take the derivative in a Markov chain? So the probability of going to a neighbor is this conductance the CXY. So if you think of okay, if this conductance is smaller, that means that that neighbor is sort of further away from you, right? It's harder to get there. So we can call 1 over the conductance is the resistance. That would be in electric networks. And the resistance is like the length of that edge. So if I want to take the derivative, it's natural to divide by the resistance, the distance. So I take the difference of the values of the function at x and y and divide by the resistance of the edge, meaning I multiply by the conductance. Of the edge. So that's like a derivative. And then I can look at the L1 norm of the derivative, which is just okay, I take the 1/2 because I don't want to, so you know, this ordering thing, like every edge will be twice. Will appear twice, so that's why I took the, so this is an unordered sum over pairs, so that's why we took the 1/2. So that's the L1 norm, just the sum. So like, you know, that's the definition. And then, so I write it in this way. So for each x, I take only the y's where fy is bigger than fx. And then this difference between you know, fy minus fx, I write as an integral, sorry, not to 1, but to infinity. I take the indicator between fx and fy and integrate that. Okay, this is a silly way of writing it. But not that silly, because so this comes out, and now we have, so that for a fixed t, I have this sum over the cxy's, where t is in this interval. So it's a sum over xy's, where fx, so t is in between fx and fy. Okay, I don't know about the inequalities. It doesn't probably matter. Maybe 1. Okay, anyway, it doesn't matter. So the cxy dt. And okay, and this is just you know, take the set where f is at least t. Take the set where f is at least t, and take all the edges that go out of it, and take the total conductance of those edges. That's this sum. And now, this is the edge boundary of a set. So the conductance of that is this. So we assume that for any set, this was at least h. So in particular, for this set is at least h. So I can just write h times 0 to infinity pi of this set, where f is at least t, dt. And sorry, I forgot to do that. Okay, right, what is this? It would be an integral of f if f was positive valued. Okay, but we can actually assume that f is positive valued. So for any f, if I take the absolute value of f and take the gradient of that and the L1 norm of that, how does that compare to the L1 norm of the original gradient. Right? The absolute values can only decrease. Okay, and how does, so by taking the absolute value, I decreased this, while for a positive thing, this will be just the L1 norm of F, and the L1 norm is the same as the absolute value because it's defined like that, right? So here I'm getting the same. Here I got, so I can assume that F is positive. Right. So this one is understood with respect to pi. Okay. Okay, just one line. So what did we get? That the, okay, maybe it's more than one line. Okay, we got something that, so the gradient, the derivative, the L1 norm of the derivative of the function is at least constant times the L1 norm of the function, just by geometry. Right? If the Markov chain had good isoperimetry, you can translate that to something about the L1 norm of the derivative of functions. But we want an L2 thing, right? For this operator norm. So how do we get from L1 to L2? Cauchy-Schwarz. So there will be a clever Cauchy-Schwarz, and I have to relate the derivative of F to this actual operator norm of P, which is also, so these are two easy things, but I will do them next time. And then I will say what the finite graph analog of all this thing is, which is expander graphs. And then I will tell you what expander graphs have to do with Kazhdan groups. And that's the plan for tomorrow. Also tell you what Kazhdan groups are. Okay, thank you.
I guess we can take a few questions.
So maybe this ultrafilter thing maybe could demystify it. One way would be to say the choice is to assign a convergence sequence to convergence subsequence to any sequence of outcomes.
Oh, yes, 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 yes. Like diagonal or something. Yes, yes, yes. But we have uncountably. Yes, yes, that's also true.
Okay, if there are no further questions, let's thank Gábor again. This is wonderful.
Thank you. Yes.